been doing. So let's start our time travel. So what we are going to talk today is something about remote sensing, data and technology, a walkthrough from past to present. So myself, Kannan, Senior Remote Sensing and GS Data Analyst at GISTEC. So what we are going to see here is whatever the data or whatever the technology that we see today like this. For example, if this is a kind of an image that we are looking into it, or if this is a kind of an image that we are looking at, where are we from? Like, for example, where did we came to this level of the high resolution images and high advanced technology? What kind of analysis that we are doing this? So all these things that we are going to learn, or all these things we are going to refresh. I hope the group is a heterogeneous group, and there could be research scholars, there could be scientists, there could be eminent personalities in the field of remote sensing and GIS, there could be professors, and there could be youngsters who are just joining the domain of GIS and remote sensing and who already done the graduation GIS. So I'm just giving a common platform where for people who are working in this domain over a decade or 2 decades, they know the technology, and it's going to be a nice, refreshing presentation. And for those who are just began their career in the field of remote sensing and GIS, or in the field of remote sensing, specifically in the domain of remote sensing, it's going to be a nice intro of how the technology has evolved over a period of time and how we are going to look into it, right? So to begin with, I'm just going to start the very basic activity or very basic fundamental thought process. What is remote sensing? So as you see, it is always said it's an art, it's a science. It can be called as artistic science, because whatever we do a data capture, we are capturing the nature, the surface of the earth. The surface of the earth, when you see from the sky, which we refer as eye in the sky, as the satellites, we are looking at different shades of the nature of the surface of the earth. So we are talking about artistic way of representing the earth. So it's a science, it's an artistic science, and we have the technology to look from the above. So we are going to see what is there on the earth, what is happening on the surface of the earth, what are the changes that is happening on the surface of the earth, what was there previously and what is not there now, or what is happening now. So we are talking about the near real-time technologies, right? So remote sensing, whenever we say remote sensing, and whenever these technologies combine, these technologies doesn't mean that we have to be there at present. The remote sensing is the science and technology of obtaining information of any of the phenomenon or any of the object without having a physical direct contact with the object under investigation. Okay, so that's why we say there is an eye in the sky. So before even the advent of this technology, we have been gifted, the human beings have been gifted with a sensor, our eyes, you see. So when you look in with our eyes is a sensor. So when we look with our eyes, we observe certain, say for example, we observe our colleagues, we observe friends, we observe new people, we understand them, we know some information. So these are all basically a kind of an information collection without even having a direct contact with a particular person or an object or an animal or a tree so we try to learn it. So that's how the remote sensing happens. Now the learning, the kind of an emotion that as a human being we perceive, that's something which is not now it's a real time. But what we are going to talk about is the collection of information, the idea of identifying and defining a kind of an information, defining kind of a phenomena, and getting into acknowledgement of what exactly happened or what happened. So to come to this level of what you see here as kind of a very nice image that you can seriously interpret and then see, wow, we can say, wow, and this technology, how it came, this is what we are going to see this. So this is the highest resolution image that is available. So to begin with, I'm going to do a walkthrough with you all, with all of your support. So hold me, and then we'll walk through from the past to present. So let's go first in the past. But before going to the past, I just want to give you a hint that for any of the remote sensing activity, the fundamental source of energy, what we are going to discuss in this presentation is the sun, the solar energy. So we are going to take pictures, as I told you, the eye in the sky, we are going to take the pictures when there is a solar energy, when there is a sunlight. So we are going to talk about something like an electromagnetic spectrum, where we are going to look into one of the visible spectrum where the pictures are being taken and the pictures are being interpreted. So we are going through the fundamental source of energy by understanding that sun is the basic source that we require to capture these images. So how it all begin? How it all begin? So it didn't begin actually from directly somebody launched the satellite. Now we know the term satellite, sensors, orbit, altitudes, everything we know. But it didn't happen on a day. It didn't happen on a second. It happened over a period of time. It happened over a period of time of people working heavily on the technology, people trying to understand how we can develop the technology. So it all started with a photograph, like the history of remote sensing began with the invention of photography. So when the invention of photography came, it was in 1038 AD. Al-Hasan, an Arab mathematician who is considered as the father of modern optics, he made a significant contribution. That's why exactly we had some kind of some sort of an initiation of the principles of optics, the visual perception in particular. So there is a book, nice book, which is Kitab al-Manazir. Sorry for if I'm spelling it a little incorrectly. So it's called Book of Optics, where there is a lot of information about the kind of what do you call, the kind of the optics, the principles of optics, how the visually things are being perceived. So he is called as a father of modern optics. So slowly things got, people started learning this, people started understanding the things, people wanted to get more innovations. Then in somewhere in this period, in 1666, I'm not going in detail for all the details, but I'm just going to catch only the few of them. In 1666, Sir Isaac Newton, probably it could, somewhere it says it is accident, somewhere it says it's basically a kind of a experiment he was doing. So whatever the case may be, he identified or he found that there is a dispersion happening when you pass the white light into the prism. This we have done in our school days, in our physics exercise. So when we have a prism and we pass a white light, it splits into different colors. It splits into violet, blue, indigo, green, violet, indigo, blue, Vibgyor colors, right? Now, when you pass those colors into the prism, it goes into a white light. So he found this dispersion of colors, which was a major breakthrough of merging to white light using another prism and dispersing of white light to different colors. Now, so the technology have been growing it, but one time in 1826, the French inventor Joseph Neffe invented the first permanent photograph. He invented the instrument, we can say, to capture the surrounding. So that was the first breakthrough of the photography. That was the first breakthrough of the photography. So starting from Al-Hasan in 1038 AD, we have been, in 1826, we had the first permanent photograph was identified. Then, the curiosity of taking photograph grown, and the people thought, okay, why are we taking photographs only on the ground? Why don't we look from the sky? How do we go from the, how do we take the picture from the sky? What is that? What is the technology that was available there? Now, the only technology that was available in 1800s, that was like a balloon. So we know that the Nadar captured the first aerial photograph that you see on the screen. And it was one of the, again, mind-blowing breakthrough that, yes, we can take pictures from the from an aerial perspective, and we can see some more areas. Still, we are not reached to an extent where people thought about interpretation, but people were more into understanding the technology, evolving the technology, or making the technology more easier, or getting through the groove of the technology. Now, what happened then from 1858 in 1903? After the photography was developed, after the cameras were built, pigeons were used to transmit not only message, but also they were put the cameras, and then they were being taking pictures. Then again, that's another level of aerial photographs that was taken. Okay, let's move forward. And the aerial photography was heavily used in the World War I in 1914. You see, after the invention of the flight, or not actually the flight, I mean, we can call it as a flight or an aeroplane that was invented, and then it was extensively used in 1914, and it was just to capture, to see, just to view, so that's where the term interpretation also came in 1914 World War II. In 1934, when a group of people, when a group of inventors, when a group of eminent personalities, scientists, research scholars, professors, try to say, okay, we are getting a lot of information from this aerial view. So what can we do? So that's why that's why it started 1934. The American Society of Photogrammetry and Remote Sensing was founded. So there were the society was formed to understand where we can move forward, how these images, a lot of images are available, how we can make use of these images, and what kind of interpretations can be done. So after seeing this, in 1849, Landsat used a terrestrial photograph. He was the first person, he was considered as the father of photogrammetry. He was the first person to use the terrestrial photograph to do the topographic map compilation, right? So, I mean, this was done manually. Later, what happened? Yeah, after slowly in the 19th century, in the late 19th century, so for example, when it was considered, okay, we can take the photographs from the area, from the skies, so things started improvising it. Then slowly the technology got developed. Now we have aerial photographs that can be picked up, and then we can do wonderful analysis. So if you are seeing this screen, wherein you have the flight strip, the flight takes the pictures. You have a flight line that can be combined together to form one image. I mean, it has taken a lot of time to come to this level, but we have this technology now currently available for taking some aerial photographs. So there is a nice article which is available as History of Photogrammetry. I would definitely recommend you to read it. There is a link that I have given you. So it tells you where from it started. I have given a brief. So it tells you where from it started and how we have came up to this level of understanding how the aerial photographs are taken, how this is processed, what are the kinds of flight line, what is enlap, what is overlap, how the pictures are aligned, and finally how the 3D content. We are going to see something like a 3D modeling of this aerial photograph, like a stereo image. How we are going to take a 3D model, how we are going to create a stereo image, and what data that we can extract from these images. So the technology has grown for the aerial photographs. Now, this is one of the interesting sample. For example, there were analog imagery and there were digital imagery. So again, the clarity on the imagery improvised with the advent with the over a period of time, right? Now, when we talk about aerial photographs, people started thinking, okay, why we are restricting ourselves to the aerial photographs? Why don't we go far ahead? Okay, let's launch something, and then we see how we let us increase the altitude and see how we can take some pictures of the Earth's surface, how it looks like. So it all started from space. The first photo from the space was given in 1946 over New Mexico. A rocket was launched. So that time the technology has already grown a little more, where the rockets were interestingly seen as one of the carriers for the cameras. Okay, we still haven't come to a kind of a taking like a sensors. It is like cameras. So they just one-time launch. They just take the pictures, and then they were able to see some kind of pictures like this in 1946 and 1947. But the actual first artificial Earth satellite and that was launched was in 1957. That was in Sputnik program. But the real application of the remote sensing data, now I'm just going to use the term from here onwards, the remote sensing data, the satellite imageries, the sensors, everything, it came when the Landsat series of imageries were open for the public or for the researchers to use. So the Landsat series of satellites, the running system of satellites from moderate resolution, optical remote sensing satellites were coming here. It all started in 1972 when the Landsat 1 was launched, and now currently we have Landsat 9 series, which is inactive. Inactive means it is taking pictures now. So this Landsat series of imageries that was taken from the Landsat sensors were heavily used, or it has been used for various domains. So if there are youngsters, if there are students, or if there are the degree holders who have just started that domain in the remote sensing and GIS applications, you can think about in any of these domains like cartography, like hydrology, like geology, agriculture. So this the perception of looking the image changed after the series of Landsats were launched. People started looking the image in a different perspective, in a different domain. There were several scientific research and applications and image interpretations were happening for all the categories, name anything, whether it is cartography, whether it is oceanography, land use, land cover, development activities, agriculture. And once the Landsat series were launched, so this technology was shared across the globe, and then the French were launching the Spot satellite. So there were Spot missions that were launched, and we have Spot 1 series to Spot 7 series, and now the remote sensing domain were growing from from a small infant child-like to a small boy or a younger boy, like this. So the Spot series were launched, and then Indian space mission started. We had so the Indian space mission were launched over a series of satellites, starting with Bhaskara to here at present is like IRS Indian Remote Sensing Satellite Series. So we had different missions, and there were a lot of images that have been captured. This is one of the images that you see, a CartoSat image of 2.5 meter and a multispectral image of the IRS satellites. Now, the Earth observation applications, for example, one of the applications that were used was a land use land cover application. So this was one of the interesting applications that you can do it using the satellite images that are available on today's over today. So this is one of the example, land use land cover changes over 2005 to 2017, and how other applications we are thinking about. So we are talking about solar energy as one of the renewable energy. So we can see how the solar energy is derived from using a very high resolution radar instruments that have been that you can be put up in the that you can put up in the satellite, and this captures the solar energy radiation over across the region, and you can see how this provides a synoptic view covering a larger areas for the larger periods, whether it is a wind, whether it is solar and wave energy source can be assessed using a Earth observation data sets. That is always possible. Or if you're talking about geology, if you're talking about earth science, yes, we still have a nice pictures that is coming up from the top, from the sky. We have satellite images that brings up images that is something similar to what I'm showing on the screen. It helps you to find, it helps you to interpret lithological, geomorphological, structural mapping. It helps to identify the spectral characteristics. It helps to identify what is on the ground, what kind of rock that we are interpreting, what kind of image that we're looking into it, So, or if you want to have some kind of a structural interpretation, whether it is a fracture, whether it's a lineament, whether it is a dike or a faults over the surface of the earth, we can still look into the images for our interpretations. Okay, then we have our own UAE National Space Program, the Earth Observation Satellite, which started with the DubaiSat 1, and then it went all the way to DubaiSat 2, and then we now have the high resolution CaliberSet 3D imagery with a resolution of 0.7 meters pan-chromatic and a 3 meter resolution of multispectral band. So the most advanced enhanced digital camera is in the CaliberSet with the fastest download and communication system, and having an automatic satellite control system with a satellite positioning technique. So we talked about the images that were taken in a small area in in USA, wherein the images were looking little more grainy. I will not say little more grainy, it was looking more coarse, for example. Let me just go back to my first image. So this is what the kind of image we had, which just hardly says anything about, or we could say anything about it. But moving ahead over the technology, now we are seeing images which are high resolution images, low resolution to high resolution images, we can say. Depending upon the usage, what we want to use, we can have images that can be of low resolution to high resolution images. And the CaliberSet is one high resolution images where we have the 0.7 centimeter, sorry, 70 centimeter resolution of high images that we are getting it. Okay, now this is one of the example. Few screen captures. Thanks to MBRSC for having nice images, captured nice images through DubaiSat 1, DubaiSat 2, and later we have these fantastic images that has been captured for this recently concluded Expo program, Expo 2020. So we have a stunning image that is coming from CaliberSet. So think of the images, how we have evolved, how the technology has evolved, how the data has been seen, how the data has been interpreted from a very coarse image to a very fine image. So the technology has involved not only the interpretation, but even the software. I'm going to show you some of the interesting results at the end of this session. But it's a glimpse of what exactly we are seeing from the past to present. So when you look at these images, let me just put you as a quick overview. So we have seen those CaliberSet images. I'm just giving you a hint of, or a quick overview of how the images were when it is a 30 meters, how the images were in a 10 meter, how the image was in a 5 meter, and how we had an image from Iconos for a 1 meter image. Then it comes to 60 centimeter image, you see. So the technology has grown. The data that you look into it, the data that you interpret into it, have evolved over a period of time, and what we look. So we can now identify the technologies in a way that we can now identify even a single, let's say a parking or a car or a lane, you know, that much the technology has been developed. So not only the data, when I say data, we have been taking pictures in a visible spectrum. You remember in the first slide, I talked about the fundamental source of energy, which is sun, and then we talked about the electromagnetic spectrum. Now, the electromagnetic spectrum, we have the spectrum from gamma rays to radar waves to short waves. Now here, most of the time, we concentrate on the visible spectrum. The visible spectrum is like green to red, right? Green, blue, red. Now we can have a difference between a multispectral and a hyperspectral data, which means when you say a multispectral data, I have an RGB visible spectrum as a broadband, or a multispectral data which has a range of blue, green, and red, which is a near infrared, thermal infrared. That is multispectral data. That is what we normally use. But if you want to use a hyperspectral data, you're going to subdivide this band of 0.5 to 0.52, a band of blue, into a number of different windows. So each and every object on the surface of the earth have a capability of either absorbing or reflecting or refracting, depending upon their nature of the object. So when as we told, the fundamental source of energy is the sun. When the sun rays or the sun energy hits a particular object, depending upon the characteristics of the object, it either emits back some of the energy out, it absorbs some of the energy in, and depending upon this, we can identify the source of this object. Now, it can vary. So when you say multispectral, we are combining, for example, if the object is of a blue color, we're just putting into this band 1 of 0.45 to 0.52. But if it is hyperspectral, we can say which blue that we are talking about, a shade of blue. Now, when you talk about shade of blue, we should also think about having a concept of colors. So when you say colors, let's say a color from 0 to 255, right? So when I say 0 to 255, let me just quickly give you one hint of what we are talking about. I'm just going to put a shade here, for example. Now, when I say a fill, I have a shade. Now, when I say all the colors are 0, I hope you are able to see my screen. When I say all the colors are 0, we say it as a black color. When I say all the colors are 255, sorry. We say the color is white. So that's a shade of colors from white to black. However, when you want to talk about these spectral bands that we are talking about, the band 1, band 2, band 3 of the images, I will show you a demo on the multispectral. Let's say if I have 255 red band, which means it only captures the red band, which means the green and the blue are 0. It will not capture or anything on the green and the blue band. But if you have a green band red, red has 255 and green has 255. Now that's a different color. It's a combination of red and green. And if you have a red as green, red, green, and blue as 255, as I told you previously, it is a white color. So when I say a combination, for example, when I say a combination of red, which means if I have a hyperspectral or ultraspectral data, which means the red itself is subdivided into multiple windows. So when the sensor captures from the satellite, it has a lot of bands that it can capture within a short span of windows, which is 0.63 to 0.69. Even that 0.63 to 0.69 can be subdivided into multiple fraction of windows. So you get more options for a lot of data to be identifying the data and its characteristics. So we are talking about a broadband, we are talking about a multispectral, we are talking about hyperspectral, and we are talking about ultra hyperspectral. So the technology here now have the data where you can have like hundreds of bands, hundreds of bands, where each and every band can be subdivided into small windows, and niche, like for example, a small objects which is having a different wavelength can be captured into the particular band set. So that is always possible. So talking about the bands and talking about the colors, when I say a color, if I say a blue color, an object is a blue color, or object is a black color, let's say, which means if I say an object is a black color, which means it has absorbed everything within it. It didn't leave out any energy. So it is completely black. What if I say if an object is in a white color, it has left all the energy and it is not storing any energy. So now the object is white color. So similarly, if an object is a blue color, so human eyes can detect maybe I can say a light blue, a dark blue, or a shade of blue, like maybe a 7 or 8 shades of blue. But system can identify n number of blue colors, like you see here, the different shades of blue color. So when I say a blue color, which means the object absorbs everything and holds only the blue color and leaves all the other colors, right? So the object appears blue. So the color is very important. And so based on the colors, we are talking about a multispectral image or a hyperspectral image, depending on the bands it has been collected. Similarly, if you are talking about black and white, as I told you, it is between the ranges. So white and black. So if everything is absorbed, it is black. If everything is left out, it is white. So this is about the spectral resolution of the satellite imagery. So now there is always a question that comes to our mind. Why so many satellites? What are we looking into it? So as we saw in the previous slides of Landsat, we have varied domains of applications, which is starting from the agriculture to the development activities to securities. So we need varied resolution, which means we need resolution of 1 kilometer image, or we need resolution of even 30 centimeter to 50 centimeter image. Now the other thing is the satellites have definitely a lifetime, you see. So when I launch a satellite, it has a lifetime, for example, 5 to 7 years, and it needs a replacement. And also technological improvisation, which means we are not only launching satellites on the higher altitude to have the Earth observation, we are also launching satellites which goes for the low altitude and then captures the atmosphere. For example, there was some satellites that were launched recently to know the atmospheric content, for example, the CO2 content or the nitrogen content. So the small satellites are launched from the academic side, from the research side, from the innovation side, and most importantly, each and every country would like to have their own satellites for the development activities and for the national securities, right? So we have a larger satellites from a macro satellites or the big satellites to a micro satellites. So satellites are important for various interpretation purpose, for various analysis, for academic to the securities. Now, when we have these kind of a satellite data sets, now what we do, previously what happened was, We used to have a satellite data. When we want to order it, it comes in a roll, actually, in a physical roll, wherein we have to open this roll, and then we have to put it on a big table, and we have to put a tracing sheet on it, and then we start interpreting it. We start drawing it. I hope I'm able to communicate you the message. So we have a tracing sheet, and then we put the satellite. People who have been in this field over 2-3 decades, they know how difficult was the time when we had to draw with those pencils, and then we have to capture those important, interpret those important features on the surface of that has been captured and printed and pasted on the table. Later, the softwares were developed, and then these softwares we are able to do some kind of a digitization. And then once we digitize it, okay, we have the satellite, we have the imageries, we have the aerial photographs, we have the aerial photos, we have digitized it. What next? You see, now I know, okay, once I see the image, I could say, okay, this is the road, this is the tree, right? Now, how do I approach further? What kind of analysis were made further? Now that comes the kind of a classification. So a traditional classification techniques were used. So with the advent of development of softwares, with the growing technologies, with algorithms, with people building up more and more nice, quick algorithms, these activities came in forefront, which means people started using the software to classify data, which means they will say, okay, classify all my water bodies, classify all my vegetations, classify all my greeneries. So what is the underlying technology here? The underlying technology is people are trying to identify each and every pixel. Now, when I say pixel, the pixel has a value. Pixel is called picture element. So each and every pixel has a value. So if it's a combination of multispectral, which means R, G, and B. So the red pixel has a value, the green pixel has a value, and the blue pixel has a value. So combining all these pixels, red, R, G, B, you are able to see the image or a particular object in the image. Now, if I have a particular object, I'm able to interpret that this particular object is, for example, a vegetation, a tree. Now I can say to the system, go and pick up all those vegetations and then tell me how much of the vegetations are there. So I'm just doing a classification. Now this has improvised. So this is what we talk about pixel-based classification. So we have the technology developed and we have got pixel. Now the current scenario is we are talking about object-based deep learning classification, you see. So we can go in a way where we can even identify what we see in our eyes. We can identify, we can develop an algorithm, or the algorithms are already available and it is getting more and more precise, more and more accurate, wherein you can say, okay, pick all my buildings in my image. Yes, we can pick the images. Pick all the trees in my images. I can pick all the trees in the images. So this is how the technology has grown. You see, if you have been following right from the beginning, where we were and where we are now, right? So we can have more and more technology coming up, more and more advancement has been coming up, and we have something called artificial intelligence. We have machine learning, we have deep learning, wherein we are trying to identify objects. So where we are identifying pixels, classifying the pixels, we are grouping the pixels as objects. And then we are saying, okay, this object is a road. Sorry, this object is a tree. This object is a building. You see this? So now that's where you're in. And then once you have that kind of an analytical results that you have it. For example, we can have something like a dashboard. We can take all those object-based analysis to identify the road signs across the highways. Let's say I want to identify all those road signs across highways, not only identifying the road signs, but also I want to pick up the symbols and the letters that is written in the road signs. So I'm doing an object detection here. I'm doing an object detection here. So across the road, how many signs that says, okay, exit. Across the road, how many signs that says, okay, go straight. Across the roads, how many signs that say go slow. So we are improvising our technology. So this can be made more of a kind of a real time also moving forward. Currently what happens is we take a pictures, we do a driving, and then we take the pictures on the roads, and then we measure with the technology, and we can get a nice kind of a road sign classification dashboard, which is already available in ArcGIS, right? So it's an object-based image analysis we call. We use artificial intelligence, we use machine learning, we call it as an object-based image analysis. Also, we can have a dashboard which is part of the, we can have it with the collector for ArcGIS, wherein you can also see an assessment, a real-time assessment you can do. A real-time assessment you can do. A manager sitting in the office can easily assess, okay, how many data has been captured? What is the data that has been validated? So this kind of a technology has been also been come up now. Okay. Or if you want to use whether an illegal well pad constructions across the petroleum sector or a petroleum field, yes, we have technology wherein you use the satellite imageries, and then we try to identify, we do interpretation based on the AI and deep learning and object-based image analysis. We try to say, okay, these are the official oil pads. These are the official oil pads. So anything away from this are illegal well pads. Sorry, it's not oil pads, well pad. We can say oil pads, we can say well pads, okay? So we can have a dashboard, we can have an interpretation, we can have an algorithm that is running behind, and we can do these interpretations based on our input data sets. So that is always possible. Okay. So now let me just go back to one of the demo. Let me just stop share here. If you have any questions in between, let me just take up the question by the time I prepare for the demo. I hope my voice was audible and you are able to hear me very clearly.
Yes.
Thank you. So let me just quickly go into the demo mode. Just give me 1 minute. I'm just going to share a screen. Okay. So talking about the technology itself, we have seen data, we have seen how the data have come, what kind of data that we have been looked into it, what was available in the past as aerial photographs or satellite imageries, and what is available now. Now, how we have been using it, from the manual interpretation, from the days of interpretation, from taking time. For example, if you have to take a whole imagery for a particular area, it may take, for example, let's say like 1 month or 2 months of image interpretation, has been reduced to week to days to hours now. With the system, high-end systems, with high GPUs, with high graphical cards, everything, with the high software, sophisticated software, the algorithms are more available. So it's all the user who has to fix in those workflows, and then he has to do the analysis. Okay. So here what I'm showing you is an interface of an ArcGIS Pro, which is a highly sophisticated desktop GIS image processing analytical software from ESRI. So this is ArcGIS Pro. So you can it directly reads the images based on the header informations. For example, if I have a Landsat image, I can directly read the header information from the ArcGIS, and I can quickly add up the data to this. And what technology I have it? Let's see. For example, if I have an ArcGIS image and I want to see a different kind of a band combination on this, then I can just quickly change the band combination. I can see a different image altogether. That's always available. Or if I want to enhance these images from this side, I can use it. So I can directly drag and drop. The technology has grown in a way that I can directly drag and drop and see the images. And I can also see what are the information that is available for me with this particular image. For example, I have the raster information. I know that this is a 30 by 30 image resolutions. And I can do all sorts of analysis. Sorry for this. I have a lot of raster functions that is available upfront, out of the box. Starting from analysis to classifications to conversions to data management. So we can directly use it. For example, if you want to use some kind of an hydrology analysis, here are the algorithms that are predefined. So this is where the technology has grown. So remote sensing, past to present, how the data and the technology has grown. This is what we are talking about. Now, previously, if I have to do this analysis, I had to do a lot of manual work, in the sense, right, as I told you, I had to do some kind of a tracing, I had to identify the water bodies, I had to see a flow accumulation, I had to see a flow directions. So this has to be people who have been into it for over a long time, they really know how it was difficult, and they also will be knowing how the algorithms are developed over a period of time, how it is easier to apply the technology more easily for different requirements. So whether if you want to do some kind of a surface analysis, we can create an aspect, we can create a DEM, we can create a slope or a shaded relief. So all this can be done with the data. So this is one example of Landsat analysis. So you can have your data that can be analyzed in a quick period of time. And then that is one example. Now this is one example for a ComSat data. ComSat is again, for example, you have a resolution of, let's say, it's over a 2-meter resolution, and you have a panchromatic image, which is, for example, let me see that, which is more of a, I think it's more of a 70 centimeter resolution. Okay, now we have a multispectral image and we have the panchromatic image. So what you can do, I can take the color from multispectral image and I can put it in the panchromatic image, because panchromatic image is high resolution. So I get to see what is called as a pan sharpened image. So now that is also possible. Instead of shading the colors for a particular feature, we can directly use our algorithms and then we can make use of it in a nice way. Now, the other thing is, for example, we have a DubaiSat. Thank you for MBRSC for providing a nice. This is one of the D2 image, DubaiSat 2 images. So we have a multispectral image of DubaiSat. We have the panchromatic image of DubaiSat, the same area. So we have the color image and we have the black and white image, and we have the pan sharpened image. So we can directly use the technology from the software itself. There are lots of tools and functionalities that are available when you are going to talk about image analysis, or when you are going to talk about working with the imageries. So we have tools that talks about change direction, that talks about classification, that talks about deep learning, or you have some images that talks about motion imagery also. You can do some kind of a multi-dimensional analysis. If you want to do some kind of weather analysis, there is a lot of multi-dimensional analysis also available. Now, after seeing this kind of an idea of imageries, we also have whatever I showed you as a demo. We have a I'm showing you as a demo. What I showed you as a slide, I'm showing as a demo. Here, if you see this, this is one example where a deep learning technology, an artificial intelligence deep learning technology were used, and all the palm trees were detected. So you can see how the area where, how the images are, and how each and every area, the palm trees have been precisely detected using artificial intelligence and deep learning. So when you use this technology, for example, I can just go and show you in the ArcGIS, there are tools that are available. Let's say, for example, a deep learning. Now you have detect objects using deep learning, classify pixels using deep learning. So you saw previously we had a pixel classifications. Now we have here also a classification using deep learning. So we have thoroughly advanced classification techniques that we have. So using this, so once you want to use this, you need to have some kind of a training. So you need to say to the system, okay, these are the palm trees. So how do you say this? For example, I just have to tell the systems that these are my palm trees. Let's say I'm just going to quickly brief you, for example. So I'm just going to select a particular palm tree like this, and then I can just say palm. So I can keep collecting these kind of. Now here, what I'm saying is, there could be a question, okay, pixel classifications and the object classification. Here I'm considering the palm as an object, wherein there can be a varied pixels, there can be a varied pixel values, but it could be a dry palm, it could be a fresh palm, but the idea here is I'm grouping it as one object. So wherever I see this kind of a canopy, so I'm telling the system take this canopy as my classes, as my samples, and then wherever you find this canopy, consider it as one object, and then give me an output. So once you have this, you are going to train it. So we are going to export as a training data set. There are different training methods that are available and different metadata methods that are available. Once you do this training, so we can do, we can provide input for this as we take samples. And there are different model parameters that are available, for example, in ArcGIS. So you can use these many models. For example, you have a single shot object detection. So that's why we are looking into the technology, how the technology has evolved over a period of time. Now we have pre-built or inbuilt algorithms that are available. So we have single shot detector, we have feature classifier, we have faster RCNN. So there are a lot of, you can do image translations, you can do a pixel classification. So, or you can have an MM detection of object detection. So once you know what exactly you are taking at the samples and what you want to make the system learn, use the particular model type. Once the system learns it based on the models that you define it, then it's about it's like no time you get all these results that are available. So you can keep it as your library. You can keep it as a sample library of all these classes. Let's say, for example, I have a palm tree over the whole UAE as a sample library. So tomorrow I already built the model. I have streamlined the process. I have built the model. So what I can do, I can just detect. So I already have the model predefined. I can now detect the objects. So I can just use detect changes, or for example, detect objects using deep learning. So I'm just going to input the raster, whatever the raster image that comes, depending upon the resolutions. You may have multiple resolutions. So you might probably have to have multiple objects for different resolutions. So for this particular resolution, if the same image comes after a period of time, for the same resolution, you can use one particular model. For different images, for satellite images, you may have a different resolution. You may have to collect some samples. You may have to have a library. Then you create that particular model. You define it. Okay. So now you detect the objects. The final object detected would be something like this. You see, each and every tree would be detected more precisely and more accurately. So that's where the object detection comes into picture. So this is the, on a quick note, this is the kind of an image analysis that we are talking about. So we started from the image where we have no idea of what exactly the image is all about, to a level where we are talking about an image where you can, or the technology where you can use the technologies, intelligent tools are available out of the box. And you can extract the results in no time currently. So where the time was taken for more than, say, weeks, now the time is maybe one day, maybe hours, depending upon the for example, you can say hardware software configurations, you can, depending upon the images that you have, depending upon the resolution you have. So there are many factors, but technology is available now. There are a lot of tools that are available now. There are a lot of algorithms that are being developed. So ArcGIS has all those tools that can be used to, for example, you can do some auto rectifications. You can do automatic auto rectification. You can use drones. However, now, yes, see this. We talked about satellite images. We talked about real photographs. We didn't talk about drones, right? Okay, drone is one interesting part of advanced technology. Now, the drone pictures are very precise, very clear, very with a very high clarity. So when you talk about satellite, if you can perceive, if the satellite covers a larger area, even on a high resolution, the aerial imagery covers a larger area, but more information. The drone covers a smaller area. So if you want to have a smaller area inspection, then drone is one of the imageries that you can. Drone imageries can be used for your analysis, for a inspection for your smaller areas. For example, there is a construction monitoring that you want to do. So when you want to monitor a construction progress, you can use drones. So every week, or if you are more precisely want, you can say, okay, how the changes happen over a period of time, in a daytime, every week. So these images can be put into this container, and then you can process the images. You can do some change detection. You can do some, as I told you, you have raster functions. You can use an automatic georeferencing, which means I can have a base map from ArcGIS itself, and I can use this base map for my georeferencing. I can do an automatic georeferencing, and I can simplify it. And there are several indices that are available. For example, there is NDVI, there is water indices, there is geology indices. So these are already pre-built algorithms that are available, and this is what the advance that I wanted to share with you actually. These are all the advanced technologies that are available that I wanted to share with you from the past to present. And we have the softwares that can do wonders. It's only that we have to plug in those workflows. So once you have the workflows that are ready, we can make this analysis, and we can do all those interpretations which is available. So we have both supervised and unsupervised classification. We have the object-based and pixel-based classifications. You can segment the image. You can take some samples. You can do the analysis accordingly. Or if you'd like to just see the image information on a particular image, you still have those information. So when you move the cursor, I know where I'm exactly moving, and when I click a particular point, I can see the spectral bands of those images that can be made available. That is always possible. Okay, so those are some of the things that we wanted to share it. So let me just wait for a few minutes. So if you want to have any questions, I can just open it for it. Can you do a quick demo on classification if you have it ready? Ah, interesting. So as a part of a demo, I was prepared for the advanced demo classification only. So I just showed you the workflow, how it happens. It takes a little time, but then yes, I showed you this one as an advanced classification. You can just use this classification technique. For example, in ArcGIS Pro, you can collect some samples on a particular area. You can export these samples, and these samples would be used on the geoprocessing deep learning tool, for example. And you can use a specific model. This model, it's a little trial and error initially, but over a period of time, once you know what kind of images that you are going to get, this model can be streamlined. So you are going to get an output model. Now, once you get an output model, you can use detect objects using deep learning. This model definitions would be made available. For example, let's say that this is a kind of a model. So you'll get this kind of a model that is made available, and you can use this models, which means this model holds all those training samples. This model holds all those training samples, and then these training samples would be combined, and then based on the shape, based on the size, based on some pixel parameters, it will identify, okay, Kannan has said that, okay, if I have the crowns like this, I have to pick up as a palm trees. So it runs through this model and picks up the palm trees. Okay, I hope that clarifies the question.
Yes. Thank you so much, Mr. Kannan. It was very interesting presentation and webinar. To be honest, I myself has learned a lot from this webinar. So to proceed, if you have any questions, please can you type it in the question and answers box below, and Mr. Kannan can answer all the questions in the question and answers box, please. Mr. Kannan, I have a question myself, if you don't mind.
Yes, please.
Yeah, when you did like a circle around the palm tree, does the software like save it as a data set or what exactly?
Interesting. Okay, very interesting. It saves as a chip image. Actually, it saves as chips as an image.
Okay, and can we export this image?
Yeah, it is export. I can just a minute. Let me just see if I can show you that actually. Just a minute. In the meantime, if you have any other questions, we can take it up.
Yes, everyone, if you have any questions, please type it in the question and answer box. If you have any difficulties, please let me know. Okay. I'm not sure if they can type the question. If you have any comments, please also list them in the question.
Let me just share my screen, Engineer Reem, just a minute.
Of course.
So that was interesting question. So I just thought, okay, I'll just quickly share the screen and show you the details. Let me, okay. You're able to see my screen?
Yeah.
You're able to see my screen?
Yes, yes.
Okay. So now what happens is it just shows as an image like this. So let me just see if I can show you. See? Okay. So now it just shows as images.
Yes, very interesting.
So it can just pick up, so you are going to do some label objects. So for example, it can just open up and let's say, see, this is one of the palm sample.
Yeah.
So what happens here is whenever you are going to export it, whenever you're going to export it, you have some kind of an image size, you know, you have some kind of a tile size. So you create a tile. So what happens is this image is cut into several tiles based on the tile size, based on the parameters that you provided. So these tiles are stored as a chip images.
Yeah, very interesting. Very interesting.
So these tiles are stored as these chip images, and these chip images are used as the samples for the models to learn. That's why you say, I'm going to train the model.
Yeah, I see.
Okay,
Clear,
so I'm just going to train the model. So now when I train the model, I'm going to give this input training data as these images, these sample images, right?
Yes.
So once I give these sample images, it trains the model and say, okay, Kannan has given me these samples and I have to identify all these similar objects. So I'm not saying images, similar objects. You see that?
Yeah, very clear. Thank you so much, Mr. Kannan. Actually, we have one question here from Ahmed. He said, regarding oil spills, is there any tool to work on to detect it?
Oil spills, yes. Depending upon, see, for example, generally the oil spills are done through the micro remote sensing. Currently, there are some technologies that are available where you can use the oil spill detection in multispectral also. Recently, somebody did one oil spill using sentinel imageries, using sentinel imageries. So let me just quickly check it. Just give me 1 minute.
I think we're running out of time.
Yeah, I'm giving. Okay. I'm just sharing the screen. I'm sharing the screen.